In the last lecture, we looked at the challenges of detecting very low level signals in the presence of noise on the ground. At the end of the lecture, we identified a product, as we called device X, which had good common mode rejection and could deal with problems where there was noisy grounds or there was a lot of stray signals flowing into the ground connections on circuit boards. And we called this Plan B. What we want to do, instead of having ground referred signals, is we will use the different signals from the transducer and detect the different signal and amplify that, and ignore any variation of a common mode signal with respect to ground. Here's component X, and in this instance here, we don't care how much the common mode signal varies because we are only going to amplify the differential signal. The common mode signal has a large gain so that the output is significant, so there's no more problems with small signals flowing in the ground connection. Because it has high common mode rejection, it doesn't care what the ground potential is, which means that it can reject any noise. And the third thing is it has an explicit terminal connected to it, which the output ground is referred to. So we can be sure that the signal at the output of this node is exactly what we want. And we call this component an instrumentation amplifier. So let's look a little at a perfect instrumentation amplifier. So the first thing is it usually has finite gain, often 100, 200, 1000 times. And it's set, this gain is set very accurately on the instrumentation amplifier by resistors built into it. It is purely differential gain. In other words, the output voltage is very close to just a function of the voltages appearing at the two inputs. And ideally, this gain is zero for common mode signals. The reference signal is usually referred to ground, although it does not need to be. You could refer it to other points in the circuit as well, perhaps a bias rail. And the sense signal is usually connected to the output in a conventional feedback fashion. The output, or the difference between the output to the reference, is a differential voltage gain of the difference of the voltages between in plus and in minus, and also a component due to the common mode voltage gain. But if we have a perfect instrumentation amplifier, ideally the common mode voltage gain would be zero. So let's look at an application for an instrumentation amplifier. And here we have a thermocouple, which is dissimilar metals, and the difference in voltage represents the temperature of those metals. And we have it connected here. We have the output here connected to a coaxial cable, and the symbol that's on the diagram there is the international symbol for a coaxial connection onto an amplifier. And here we have a typical coaxial cable that would take the signal from the instrumentation amplifier to perhaps a digital processing unit to further process the signal. We've already been very careful and twisted the two wires together of the thermocouple to avoid any magnetic pickup or any electrical pickup that may happen on the route from the thermocouple until the inputs of the differential amplifier. We've connected the reference to the ground and also to the output connector. So the voltage between the inner and the outer of the coax cable is the true output of this amplifier. And in this instance here, we've used a resistor, which is a large value resistor, just to supply or bleed away any bias currents that's required by the amplifier. Because a thermocouple has got very low resistance through the wiring, the single amp resistor will actually provide the bias current for both inputs. And the design of this circuit here is pretty much immune to any voltage appearing on the ground signal. So it's only going to amplify the difference voltage. Now we can improve this slightly by actually making the improving the symmetry here. And here we've actually incorporated two resistors to supply the bias currents to each, which means that from a thermocouple, transducer standpoint, the input at both in plus and in minus looks identical from an electrical standpoint. And it has a relatively high resistance to the ground, which is what we want. If we were actually practically designing this, we would actually incorporate a low-pass filter, because temperature is not going to move very quickly, and that will actually filter out any of the noise that you may pick up from RF or from magnetic influences around the wiring. And that's what you would see in a real implementation of an instrumentation amplifier for practical use. I have uploaded some examples of that with particular emphasis on audio amplification, where you can see the low-pass filter designed to reject any of the RF noise at the inputs. Let's have a little look about common mode rejection and how this is defined in an instrumentation amplifier. So first of all, we have the output, which is referred to the reference, and we want it to be a voltage gain, AV, times the difference of the two voltages appearing at the inputs, in plus minus in minus. And ideally, we would only get an output signal in response to that difference. But because circuits are never perfect, we may have a contribution from the common mode voltage that's appearing at the inputs, which is the average voltage at in plus and in minus. Let's look at some of the numbers around our circuits and see what they actually mean. So in the first example here, we've got 1 volt appearing at both inputs, and because we have a perfect instrumentation amplifier, the output voltage will be 0. In the second example here, we have got 1 millivolt appearing at the input, so the output will be 1 millivolt times the differential gain of the instrumentation amplifier. And finally, we have 1 volt on one input and 1 volts plus 1 millivolt on the other input, and the answer is the same. We would get 1 millivolt times the gain of the instrumentation amplifier appearing at the output. It would totally reject the signal that's common mode appearing at the input. That's the perfect instrumentation amplifier. Unfortunately, because we're dealing with real components and real amplifiers, we can never get a perfect instrumentation amplifier. And a change in the common mode or average voltage at the input will always give rise to a change at the output. Our challenge is to design that change to be as small as possible while maintaining the differential output as large as possible. This gives rise to the concept of common mode gain, which is the average voltage, and in most instrumentation amplifiers we would get our differential gain will be much larger than our common mode gain, and we define a concept called common mode rejection ratio, which is a division of the differential gain divided by the common mode gain. Let's go back to our instrumentation amplifier and look at what happens when we actually have some common mode gain and differential gain. So here we've defined the differential gain as 100 times, and we've defined a common mode gain of about 0.3. So calculating that out, we have a common mode rejection ratio of 333 times, which is 50.4 decibels. Now let's apply our three scenarios. So in the first one here, we have 1 volt being applied at both of the input signals, and that gives rise to a 300 millivolt signal at the output because our common mode gain is 0.3. So the average input voltage is 1 volt multiplied by the gain of the common mode, which is 0.3, so we get 300 millivolts output. Let's look at the situation where we apply 1 millivolt. When we apply 1 millivolt to the input and 0 on the other one, we land up with an amplification of very close to 100 millivolts. Now that's the signal we actually want. That's a different signal there. Technically, there should be a small error there because the average is actually half a millivolt. But ignoring that, it's going to be very close to 100 millivolts, a purely differential amplifier. But let's look at the third scenario where we have 1 volt on one input and 1 volt plus 1 millivolt on the other input. We still have a differential input of 1 millivolt, but in this instance we land up with a 400 millivolt output voltage, which equals 100 millivolts from the voltage that we detect from the different signal plus 300 millivolts from the common mode signal. So we can see that if we have an input of 333 millivolts on each of the input, would give exactly the same voltage appearing at the output as a differential signal of 1 millivolt. So with a common mode rejection ratio of 333, the minimum voltage signal we could detect at the output is 1 millivolt. If the common mode voltage is 1 volt, as the example we've shown here, the minimum detectable signal at the output is 3 millivolts. So we would have to have, in the presence of a 1 volt common mode voltage, we would have to have a 3 millivolt differential voltage. The minimum detectable signal is assumed when the error signal, due to common mode or any other issue, is the same as the real or the wanted signal. Hopefully that now gives you an understanding of how the instrumentation amplifier works. In the next lecture, we'll go on to look at how we actually design instrumentation amplifiers.